I'd like to wrap up our study of limits as x approaches finite values by covering three important limits. These are some limits that we're going to need to use later on, and we just want to understand what they are and then put them in the category of known limits. You'll notice that all three of these limits we're interested in have a similar form. A function evaluated at x minus that same function evaluated at 0 and then divided by x. We do that for the sine function, for the cosine function, and also for the 2 to the power exponential function. Let's start off with the sine function, see what this limit is. Well, the first thing I would say is to notice that the sine of 0 is in fact 0. So what this function is really asking about is what is the limit as x goes to 0 of sine of x over x. Certainly not a known limit. We're going to add it to our list of known limits, but not there yet. What about graphing it? Let's try that. I've put this function, if you go back and look at the y, sine of x over x, into the calculator, and here's the graph. It's very pretty, actually. Let's try the trace of it to see what height it reaches. Oops. It's not what I wanted. To see what height it reaches as x approaches 0. Well, when x is 0, the height is undefined. That should come as no surprise. But just a little to the left, the height is 0.98. And just a little to the right, the height is actually about 0.99. So if we had to guess, we'd probably guess that the height is going to be 1 as x approaches 0. Now, we can prove what the height is exactly by using a special case of the sandwich theorem, but that's going to be covered in a separate video. And so in this first case, we're just going to say, based on the sandwich theorem and graphing gives us an intuition that the limit is 1. And if you watch the other video using the sandwich theorem, you'll see that we can prove that that the limit is exactly 1. And so that's our first one. That's a limit, a known limit that you should memorize and add to your list. All right, now what about this one? Well, again, we can look at the same issue here. What is the cosine of 0? Well, in this case, the cosine is 1. And so this is really asking us to find the limit as x approaches 0 of cosine x minus 1 all over x. Again, it's not a known limit. We can graph it. Let's take a look at that. I've also put that in, but let's go back and we'll turn off our graph of sine x over x. We'll turn this graph on and see what we get. Well, again, a fairly interesting looking graph, but as we see using the trace, as we get close to 0, well, at 0 it's undefined, but as we are just a little to the left of 0, it's a 0.13. Just a little to the right of 0, negative 0.13. It might lead us to conclude that its limit, meaning what happens to the height, right as x goes to 0, would be 0. But this one, we don't have to just rely on graphing. If we were to use the limit laws, of course, we would get 1 minus 1 over 0, and that would be 0 over 0 in indeterminate form. But in fact, there's an algebraic simplification that we can do to solve this one. And that is, we're going to multiply it by cosine x plus 1 over cosine x plus 1. Now, if you ask why it was that I did that, it's because I saw a difference of squares pattern that was possible. But that's probably not something you would have guessed right off, so I wouldn't feel bad about that part. But notice how we can rewrite this. So just sit back and enjoy on this one. This is just cos squared x minus 1 over cosine x plus 1. But cosine squared x minus 1, well, hopefully you remember something from your trigonometric days, and that is that the sine squared of a number plus the cosine squared of a number equals 1. So cosine squared minus 1 is negative sine squared of x all over cosine of x plus 1. Now what about the limit of this as x goes to 0? Well, here we can use the limit laws. We did an algebraic simplification. We used the limit laws. We can turn this into sine of x. Well, first the quotient limit law, then the product limit law on top, and the sum limit law on the bottom. What's the sine of x? When x is 0, well, it's just 0. So we get 0 squared, that's 0, all over cosine of x is 1 plus 1, 0 over 2. So we've proven that the limit of this second expression is 0. Again, you want to add this to your list of known limits. When you see sine x over x, you should know that that has a known limit of 1. When you see cos x minus 1 over x, you should also know that that has a limit of 0. Again, in both cases, as x approaches 0. Now let's turn to this last one. 2 to the x minus 2 to the 0 over x. Obviously not a known limit yet. And let's try graphing it. Again, I've put it in ahead of time just to save a little time. So let's turn off the second function. And let's graph this third function. See what it gives us. Hard to say just quite what that is, but let's take a look at trace. And when x is 0, it can't compute it. That's an indeterminate form. When x is a little less than 0, it's about 0.63. And when it's a little greater than 0, it's about 0.76. So I'm saying it's a number somewhere around 0.7. So this limit above is something like 0.7. Well, that doesn't seem all that interesting, so maybe we should also try to see if we use a different number as the base. What about the limit as x goes to 0 of 3 to the x minus 3 to the 0 over x? Remembering, of course, this was 1. I guess I should have pointed that out. This is also 1. Well, I've also put that in the calculator. Let's try that instead. So we go back, turn off the 2 to the x function, turn on the 3 to the x. Let's graph that. Looks kind of like the 2 to the x function, but maybe a little steeper. When we put on trace, right at x equals 0, we get indeterminate. But a little less, we get 0.95. A little more, we get 1.3 almost. So it goes up pretty quickly. Maybe it is I don't know, something like 1 point, that'd be about 1.15. Well, neither of those looks all that interesting. What's the point here? Well, here's the thing. When you plug in 2 here and you take the limit, you get a number around 0.7. When you plug in 3 here, you get a number around 1.15. That suggests that there's a number between 2 and 3 where it would come out to exactly 1. And so maybe we don't want to look at this limit. Maybe instead we want to look at the limit as x goes to 0 of some mystery number to the x minus that same mystery number to the 0 all over x. Well, if you want to test that out on the graphing calculator, what you have to do is you have to make the mystery number your variable. And we make this number something that's really, really close to 0. Let's make it 0.0001. Okay. Now I've put that into the graphing calculator. Let's have a look here. And we'll turn off the last one that we used. And let's go all the way down. Put it in down here. Notice what I did. The mystery number is the variable. I've replaced x not with the limit as x goes to 0, but a number very close to 0 by some measure, minus 1 over that same number that's very close to 0. I guess I should, let me just put this in here. Wherever we see an x, we're going to put in a 0.001. We just want to get an approximation and see what mystery number would give us 1 as the output of that limit. Alright, so back here, that's our function, and that's the one that we want to turn on. Okay? Well, rather than graph that, I'm going to go straight to the table for that. Okay? So I put in 2, we get about 0.693. I put in 3, we get about 1.098. So I put in 2.5. Well, I get a number that's just slightly less than 1. So I try 2.75. Get a number that's just slightly bigger than 1. I put in 2.71. It's getting closer. Finally, I put in 2.7182, and obviously this would be the result of a lot of trial and error if I had to do this while you were watching. I did some of these ahead of time. But I'm sure you could recreate this. You could keep plugging in different bases into this expression and see which base, see which mystery number, gives you a limit that seems as close to 1 as you can get it. Well, I hope you recognize what we're seeing in this mystery number. Okay? This mystery number, 2.7182, and it goes on, 8, 2. If we'd kept going, we would have found that the mystery number is the number that we've called E all along. So, what I'd really like you to learn is 3 known limits, namely sine of x over x in the limit as x goes to 0, that's 1. Cosine x minus 1 over x in the limit as x goes to 0, that's 0. And there is a number that when we write e to the x minus e to the 0 over x in the limit that x goes to 0, that number is 1. In fact, we could use this as the definition for e. And then we could work backwards and show that this definition for e actually gives us the same e that we got from using the continuously compounded interest formula. So those three known limits should be added to our list. I think that's pretty neat.